we defined velocity as the derivative of position, the limit of delta x over delta t as delta t approaches 0. Velocity itself can change. A car speeds up, slows down, or reverses. The rate at which velocity changes is acceleration. It follows the exact same limiting procedure, applied one level higher. Consider a body moving along the x-axis with velocity component v of t. After a time interval delta t, the velocity becomes v of t plus delta t. The change in velocity is delta v, defined as v of t plus delta t minus v of t. The x component of average acceleration over this interval equals delta v divided by delta t. In full, that's v of t plus delta t minus v of t all over delta t. This measures the overall rate of velocity change across the entire interval. The SI unit is meters per second squared. Now look at a graph of v of t versus time. The curve bends as velocity changes. Pick 2 points on this curve, at time t and at time t plus delta t. A straight line connecting these 2 points is a secant line. Its slope, the rise delta v divided by the run delta t, equals the average acceleration over that interval. Watch what happens as we shrink delta t. The second point slides toward the first. The secant line rotates, approaching a tangent line touching the curve at time t. The slope of that tangent line is the instantaneous acceleration, the acceleration at one specific moment, not averaged over any interval. Here is the formal definition. The x component of instantaneous acceleration at time t equals the limit as delta t approaches 0 of the quantity v of t plus delta t minus v of t, all divided by delta t. This limit is exactly the derivative of velocity with respect to time, written dv over dt. In vector notation, the instantaneous acceleration vector is a of t times I hat, pointing along the x-axis. Notice how this parallels the way we defined instantaneous velocity. We simply replaced position with velocity in the difference quotient, applied the very same limit, and out came acceleration. The mathematical machinery is identical, only the physical quantity being differentiated has changed. A common misconception: acceleration means going fast. It does not. Acceleration measures how velocity changes, not how large velocity is. A jet cruising at a steady 900 km per hour has zero acceleration. A car pulling away from a stoplight accelerates strongly despite moving slowly. Equally important, zero acceleration does not mean the object is stationary. It means velocity is constant. The object can move at any speed. As long as that speed doesn't change, acceleration is zero. One more connection. Velocity is the first derivative of position. V equals dx dt. Acceleration is the derivative of velocity. A equals dv dt. Combining these, acceleration is the second derivative of position. Equals d squared x over dt squared. Differentiate position once to get velocity. Differentiate again to get acceleration. This derivative chain is the backbone of kinematics. Each level captures a different aspect of motion, where the object is, how fast it moves, and how rapidly that speed is changing. Let's walk through example 4.3. The position function is s equals s naught plus 1/2 bt squared, and the velocity component is v equals b times t. We want the instantaneous acceleration. Apply the limit definition. A equals the limit as delta t approaches 0 of v of t plus delta t minus v of t, all divided by delta t. First, evaluate v at t plus delta t. Since v equals b times t, replace t with t plus delta t to get b times the quantity t plus delta t. This expands to bt plus b times delta t. Now build the difference quotient. The numerator is bt plus b times delta t minus bt. The bt terms cancel, leaving b times delta t. Divide by delta t. The delta t factors cancel and the ratio equals b. Notice that b is a constant. It does not depend on delta t or on t. So the limit as delta t approaches 0 is simply b. The acceleration equals b at every instant. Constant acceleration. This makes physical sense. The velocity, v equals b times t, is a straight line on the velocity time graph. A straight line has the same slope everywhere, and that slope is b. Three results tie this section together. Average acceleration equals delta v over delta t, the secant line slope on the velocity time graph. Instantaneous acceleration equals dv dt, the tangent line slope, found through the same limit that defines velocity. And acceleration is the second derivative of position, d squared x over dt squared. One procedure, applied twice, builds the full kinematic picture from positions through velocity to acceleration. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.